And we are now moving on to homework 12, your final homework, which is going to be on waves. So first of all, what is a wave? You guys have all seen a wave, but if you're asked to actually say what is it, it's not so easy to say what it is. And here's my best description. It's a traveling disturbance. So if you have some kind of material, like a string or water or something, it's a disturbance that travels within it. It carries energy, but it does not carry matter. There's no actual physical stuff that goes along with it. To give you an example, let's say you're shaking out a carpet to get off the dust or the dirt, okay? You're sending a wave from one end to the other, right? You don't have to worry about the pattern of your carpet going off the end of it, right? You shake it and suddenly it's all white, okay? Nothing goes with the wave. Its disturbance moves, but it doesn't actually carry physical stuff with it. That's actually true of all kinds of waves, water waves, for example. Now, breaking waves is a different story, but if you take a look at just some kind of rolling waves out in the ocean, they don't actually take any physical stuff with them. What's your evidence for that? Go ahead and jump in, okay? If a wave comes by, it goes right through you, okay? You might do this. Well, so are the water molecules around you, right? They're not actually going with the disturbance. The disturbance is passing by. It's always being made out of what is locally the stuff that was already available, okay? Another example, a sound wave. You can hear me right now. Why is that? I'm putting a disturbance into the air. But you can't smell my breath, right? It's not actually the molecules in my mouth that are traveling to your face, okay? So it's just a disturbance in the air between us, which is carrying that sound. So there are two types of waves that we'll look at: transverse and longitudinal. So a transverse wave is probably what you most typically associate as a wave. It looks like this. The motion and the disturbance are perpendicular. So for instance, if you look at a wave on a string, you put a wave into a clothesline, it might be horizontal motion, but the disturbance is a vertical disturbance. Okay? So these are perpendicular. An example of this would be a wave on a string. There's another type of wave that you can have called a longitudinal wave, and I've brought this kind of big slinky because I can actually, hopefully, show you both kind of waves on this. So if we could have a, oh, there's a knot there. Let's not have that. So if you wouldn't mind volunteering, you'll probably have to get out here. I can try to show you both kinds. Maybe stand the other side of that table. I can try to show you both kinds. So here's your typical transverse wave. So you can see the motion is horizontal. Pull it a little tighter. You can see the motion is horizontal and the disturbance is vertical, right? That's your typical wave, and you probably agree that I'm not taking this piece of metal and sending it over there, right? It's just carrying energy but not matter. I'm going to also try to show you a longitudinal wave. I'm going to pull this back like this. Let me move forward a little bit. I'm going to pull this back like this. And there's a compression disturbance. You see that? So I'll try it again. See that? So that's a a longitudinal wave. Thank you. So I'll try to draw what you just saw. I don't know why I suddenly got a blue marker. That's all right. So the motion is this way, and the disturbance is actually along the same axis. So it's like a compression disturbance. So the disturbance is parallel to the motion. An example of that is a sound wave. So my vocal cords are creating regions of compression in the air that those regions are getting to you, and then they're affecting your eardrum. That's how you can hear what I'm saying right now. Okay? Now it's going to turn out that we're going to focus initially on transverse waves, I think just because they're a little more intuitive. But we're going to find that when we go over to longitudinal waves, it's not a huge difference. It's almost like kind of just a cosmetic difference. We need to make a few concessions for the fact that they're longitudinal, but not really a whole lot. Okay? Now, one thing I am going to stay away from is water waves. Water waves actually turn out to be a combination of these two. Okay? Water waves, if you've ever been out in the ocean, you kind of notice that they're called rolling. They go like this, right? You kind of almost end up going in a circle, right? So they have a part that lifts you up and down, but they also have a part that makes you go back and forth. And so that makes you have that rolling motion. So we don't want to mess around with water waves as much as it might be one of your more intuitive ideas of waves. They're actually a combination of these two types. Okay? So we're going to focus at first, when we start to ask what the wave travels on, we'll probably do a string. So that'll be kind of our main system that we look at. Okay, any questions before I go any further? Yeah?
So would longitudinal waves just be like vibrations?
Well, you can make both of these with vibrations. It's just whether the vibration is like this or whether the vibration is like this, right? So it's just whether you vibrate the medium perpendicular to the direction of the waves or parallel to it. Does that answer your question?
Yeah.
Okay. So when you say vibration, that means just some kind of oscillation, right? So it depends on which direction you're going to make the oscillation. Okay, so first things first, we're going to focus on periodic waves. Now, what I just showed you on the slinky, or the long thing I just showed you, those are what we call wave pulses. They're kind of isolated, lonely, single things that are moving along by themselves. We want to have a whole bunch that go along like that. So not just a single isolated wave pulse, but rather the whole kind of sequence of them. So what we should do, man, I can't draw. I was trying to draw this sort of evenly. I want the exact same thing repeating over and over again. Maybe you can draw it better than I can. So the first things first, just nomenclature. Just what's the lingo? What's the lingo for describing the wave? First of all, this right here, I call this the wave equilibrium. So for instance, if I had a string and I wasn't putting a wave into it, then that's where the string would sit. Okay? So if I want to put a wave into it, a periodic wave, I have to then wave my hand up and down around that equilibrium. Okay? The maximum height highest point that the wave gets from equilibrium is called the crest, and the lowest point is called the trough. Those are just everyday English words, so you may already know them. But of course, crest and trough are in the eye of the beholder, right? If you're standing on your head, then to you, the trough looks like the highest point, so you call it trough a crest and a crest a trough. So this is just when you're looking at a particular orientation, you call what you think is the highest the crest, and what you call the lowest is the trough. So, and those, by the way, are equidistant from the equilibrium. We're only going to look at waves which are symmetric. So we call the distance from the equilibrium to the crest or to the equilibrium to the trough, we call it an amplitude. So A equals amplitude, units, of course, of meters. Please note that the way that the amplitude word is used, I briefly touched upon this when we were doing simple harmonic motion, oscillations. I'm using it the exact same way. Amplitude there also meant from the equilibrium to an extreme. So don't forget, if you're measuring the total height from top to bottom of a wave, that's actually 2 times the amplitude. Okay? Now, I'm using the same word for this and for oscillation because it turns out there's a lot of connections between this and simple harmonic motion. So there's a deep connection between simple harmonic motion and waves, which I'll get into shortly. So first, let's get the other terminology things out there. We have amplitude that describes the physical dimension this way. But we also need to describe the physical dimension this way. Now here, we can't really describe the total length of the wave because it just goes on and on. So instead, we talk about the length of one repeating unit, which we call wavelength. So we call this the wavelength. That's the Greek letter lambda, if you don't know it. And that's the wavelength, also measured in meters. That is the length of one repeating unit of the wave, and so it's really important that you measure it carefully. And don't mistake something that's not one repeating unit exactly for this. Now the test for whether or not you have a wavelength, so one repeating unit exactly, is that all properties of the wave have to reset. So you know you have measured one wavelength exactly when you are looking at a part of the wave which is exactly identical to the one you started measuring from. So there is a number of different ways to do this, one of which is what I drew there. It's crest to the next crest. So it looks like this. So you can see that the two parts, the wave part that I started at and ended at, is exactly identical. Not only is it at the same height, but the wave looks the same. It's flat in both cases. And another test that you can have is if you put this back to back, will you get the whole wave? So if I put this back to back to back to back, that's the whole wave, right? So crest to crest is fine. It's a perfectly fine way of measuring wavelength. Trough to trough is also fine. It gets a little tricky though, and this is where students might get confused, is to go, let's say, from equilibrium to equilibrium. That's not okay. Crest to crest is fine, trough to trough is fine, but equilibrium to next equilibrium is not fine. Here's how I know. Yes, the wave is back to the equilibrium, but this is not the same as this, right? And if you put that back to back, that's not the wave, is it? So here you have to not only go back to equilibrium, but go back to equilibrium with everything being the same as before. And that's also a wavelength, and if you put that back to back, you will get the whole wave properly. Okay? In reality, there's no special magic way to measure this. You can start any point in the wave you want, here. If you want, start measuring there. But then you have to end of your measurement at the exact same next identical part of the wave. If you did that, you would get the same length. Okay? So crest to crest is just kind of usually my preferred. I like crest to crest for some reason. Trough to trough is fine. Equilibrium to next identical equilibrium is fine. Really any part of the wave you can start measuring as long as you then stop measuring when you get to the exact same point. Next one. So that is it for the physical dimensions, amplitude and wavelength. They describe the distance both along the wave motion and perpendicular to it. But that is definitely not the end of the wave properties. First of all, the wave speed. That's one I've already mentioned. And then there are also several properties that you can talk about if we put kind of an eyeball in the sky. I'm not sure if I've done one of these for you before, but this is just showing perspective. It's supposed to be an eye looking down. So that's the eyeball in the sky, which is going to sit at a fixed point and watch the wave passing. There are several quantities that that person could describe about the wave. So t is called the period. Of course, we've seen that in several other contexts before. We know it as the time for something that repeats over and over. A period is the time for one of those cycles to pass, right? We've seen it in orbits, right? Period is the time to go around once. We've seen it in simple harmonic motion. The period is the time for one complete oscillation to happen, right? So this is the time it takes for one cycle to pass. And one cycle in this case is one wavelength. So for instance, if I'm counting my wave in terms of crests, I'd start my timer when one crest passed, I'd stop it when the next crest passed, and then I would have measured a period, right? The period is the time for one wavelength to pass. Again, if I'm counting crest to crest, then it's the time for one crest to crest to travel past the fixed observer. Another thing, and this I could have already introduced in the simple harmonic motion unit, another way to characterize this is oscillation or any kind of repeating motion is in terms of frequency. In fact, I could have introduced it all the way back when we were talking about orbits. Anything that has a period also has a frequency. So what is a frequency? Frequency is going to be how many cycles pass per second. It's just another way to talk about something that's passing by. So think of it like a period. It says, okay, I am going to wait here as long as it takes for a full wavelength to pass. And I'm going to time that. That's what a period is. It's the time it takes for one wavelength to pass. But think of it as frequency as I'm impatient. I don't have all that time, okay? I'm going to be here for exactly 1 second, and I'm going to count how many cycles pass, even if it's just a fraction of a cycle. I'm going to count how many pass in that 1 second I have to spend on this endeavor, right? Does that make sense? So instead of giving all the time you need for one cycle to pass, instead you ask how many cycles pass in a 1 second time span. Okay? So I'll give you an example. If the period, it takes 2 seconds for a whole wavelength to pass, how many wavelengths am I going to get in 1 second? I'm only going to get one. 1/2, right? So if it takes 2 seconds for a whole cycle to pass, that means I only get half of one every second, right? Now let me point out that while it's almost never written this way, when we say the period is 2 seconds, what we mean is 2 seconds per cycle, right? It takes 2 seconds for one cycle to pass, right? So if it takes 2 seconds per cycle, then I'm only going to get a half a cycle every 1 second. Now if you look at these two numbers, right, 2 versus a half, units, seconds per cycle, cycles per second, it of course suggests what about these two things? What are they? They're just inverses of one another. So frequency and period are just flipping the question on its head. One is how many seconds for one cycle to pass, one is how many cycles pass in 1 second. So that may be easy to tell here, except for the fact that in the period, the per cycle is never really indicated. That's implied in what period is. That's why we don't call it time generally. We call it a capital T. That implies it's the time it takes for one thing to happen. And this is also further obscured, and I should mention that cycle isn't really a unit, right? It's just a number of stuff, one thing. So over here, the units of frequency is properly actually inverse seconds, right? Cycles in the numerator isn't really a unit. The units for this are inverse seconds, and that actually gets a name. It's called a hertz. Okay? So the units of period are seconds, and the units of frequency are hertz as a shorthand for inverse seconds. So normally, it's not as easy to tell that they're just reciprocals. Okay? So that does it for the fundamental properties of a wave. The physical dimensions, amplitude and wavelength, and then the properties of the wave that an observer could see as it moves, its speed, its period, and its frequency. And so the next order of business now is to try to come up with some interrelationships between these guys. So there are some. Are there any questions before I move into that? Okay. So let me get into that a little bit. Let's talk about wave speed first. Actually, before I get into the interrelationships. Now the wave speed, that is of course measured in meters per second. And that is for us determined by the medium only. Now if you don't know what the word medium is, there's another meaning besides small, medium, large. Medium is the stuff that something travels on, right? Mass media, right? That's the plural. Right? Information travels on TV, newspapers, radio, mass media, right? So this medium, or you think of a psychic, right? Like a medium, okay? And supposedly they are conduit for stuff traveling. Just a lot of baloney, I guess, is probably what mostly it is. So the medium is the stuff the wave travels on. Okay? So it means that if you want to know how fast a wave travels, you need to know what it's traveling on. That's the only thing you need to know. It doesn't depend on the amplitude, the frequency, the wavelength. You don't need to know about the wave itself. You need to know what it's traveling on. So if you want to know how fast a water wave travels, you need to know about the water. If you want to know how fast a wave on a string travels, you need to know about the string. Okay? All right? Now this is not entirely true. Sometimes this medium, the wave itself matters, but for us, when we look at waves, we look at relatively small waves, and for small waves, the medium only matters. So let me give you the wave on a string equation. That's the system we'll look at most first. And this is going to definitely be pulled out of the hat. I have no justification for this formula. So I'm going to take some time to explain its properties. F is the tension in the string. Why am I using F for tension? I used to use T. Well, I don't want to mix that up with period, so using next fix is the best thing. I'll use F because tension is the force, right? The mu is the mass per length of the string. It's the string's mass divided by its length. If you want to, you can call it linear mass density to be fancy. Linear mass density. It's not regular density, right? Because regular density is mass per volume, right? This is mass per length. So we call it linear density just because to be fancy, okay? Now, if you looked at these things, you put in the units, tensions in newtons, and then mass per length was going to be kilograms per meter. And you worked all that out, that does come to meters per second. That's, of course, no proof that it's correct. There could be a factor of 2 in the front, and units wouldn't figure that out. So you're going to have to just trust me that this is correct. Okay? But let me explain why. Okay? So let me explain why this makes sense. So here I have a bit of string. Let me draw right here. Here's my bit of string. And I'm going to take a chunk of string right here and figure out what is it that causes that piece of string to be in motion. Well, of course, it's because that piece of string is not in isolation. It's pulled on by its neighbors. And we know that tension always pulls, right? So it's going to be along the rope. It's going to pull like that. Now, if you had to do a vector addition of those two, what do you think the result would be? What's the direction of that force? Straight down, right? The horizontal components cancel, the vertical components add. The net force is going to be like this. And in fact, this piece of string is therefore just going to oscillate up and down. In fact, if this is the equilibrium, that piece of string is just going to be pulled up and down. So remember that actual piece of string does not move with the wave, right? It just oscillates in place. In fact, it's going to turn out that this oscillation is simple harmonic motion. So any given bit of the medium actually is in simple harmonic motion. Which seems a little odd, but think about it like a wave at a sporting event. You guys seen the wave? Everybody goes like this, okay? Now you might say that's like a wave. That is a wave, okay? That's a traveling disturbance. You see it moving along, right? Now when you're jumping up out of your chair, you're not going at constant velocity, I assure you, right? It's a little harder to get up and then kind of get into it and then go faster, right? So the individual people definitely don't have a constant velocity, but everyone's reaction time is about the same, right? So when you see the guy next to you get up too. That's how the wave is created. It's from a bunch of particles that are oscillating up and down slightly out of sync, right? Slightly delayed from one another. And that's when you see that the wave can go around the sporting arena, right? And it moves at relatively constant speed, even though nobody is actually moving, no one person is moving at constant speed. So the speed of the wave might be constant, but the speed of the actual individual particles is not. It has a typical simple harmonic profile. In fact, where are you going the fastest?
Equilibrium.
Equilibrium, and what's your speed of your particle here?
0.
0. You got to turn around and go back the other way, right? So you got to stop. So we call this the transverse velocity of the medium, and that is most certainly not constant. In fact, it's your classic simple harmonic motion profile. But let me point out in this formula that if you increase the tension, the speed of the wave will increase. It makes sense, because if that piece of string is jolted down very hard with a large restoring force, well, the crest has better move on, right? That much further, right? Or that much faster. If this gets pulled down violently to equilibrium, that means the crest is long gone, right? Okay? Now, the other important thing is, of course, how much mass does this particle have, right? Because you can apply a large net force, a large restoring force, but if it has a lot of mass, it's not going to accelerate as much. So it's going to have more inertia, and it's not going to come down as fast. And so you can see here is that if you have more mass per length, then the wave travels slower. So this is like your restoring force, and this is like your inertia term. So it all basically comes down to is F net equals ma. The restoring force comes from the tension of the string, and the mass per length tells you about how much inertia is contained in any piece of string. So we'll come back to that on Friday. That's it for today.